K-invariants. Yeah, to have a community spirit, please keep your cameras on if you're not shy, and please ask questions in the chat or with your microphone if you have any. And yeah, so please begin.
Thank you very much for the introduction, and thank you for the invitation. It's my great pleasure to speak here. Let me share the notes of my talk in the chat. Let me share it again. Yeah, so that you can read my notes back and forth during my talk as you like. And also, please do not hesitate to interrupt me whenever you want to make comments or ask questions. The title of my talk is Non-Archimedean Quantum K-invariants. It's joint work with M Porta. So here is the plan of my talk. I'll start with by introducing non-Archimedean, derived non-Archimedean geometry, and then I will explain the representability theorem in this setting. After that, I will introduce the modular stack of non-Archimedean stable maps and some Gromov compactness result. And by the end, we will discuss, we will define non-Archimedean quantum K-invariants and study their properties. Okay, so. So before talking about derived non-Archimedean geometry, let me begin with a brief history of non-Archimedean geometry. Non-Archimedean geometry originated from the year 60s when John Tate, motivated by his study of the uniformization of p-adic elliptic curves, he introduced the notion of rigid analytic spaces, and that's the start of rigid analytic geometry. After that, there are many subsequent developments. So first, in the year 70s, under the suggestions of Grothendieck, Michael Renaud introduced the theory of formal models for rigid analytic spaces. And thanks to formal models, we are able to borrow a lot of techniques already developed in algebraic geometry into the study of rigid analytic geometry. Then, in the year 90s, Vladimir Berkovich introduced the notion of Berkovich spaces. So, unlike rigid analytic spaces, which only have a Grothendieck topology, the Berkovich spaces possess genuine underlying topological spaces which are locally compact. So they are much closer to our intuition for analytic spaces. And thanks to this new idea, Berkovich was able to develop the theory of analytical homology for rigid analytic spaces. A little bit later, Roland Uber introduced the notion of adic spaces. This is a vast generalization encompassing formal schemes, rigid analytic spaces, and much more. And also, it is a foundation for perfectoid spaces, which has found remarkable applications in p-adic Hodge theory. So this is a very brief overview of the history of non-Archimedean geometry. And all these theories, they offer different viewpoints and treat slightly different like setting. But when we restrict all the theories to rigid analytic spaces, they are more or less equivalent. Nevertheless, there is one special feature of Berkovich spaces that I would like to mention. So Vladimir Berkovich, he constructed for these non-Archimedean spaces with respect to his underlying topological space, he constructed piecewise linear subsets called the skeletons. So non-Archimedean spaces are in general very complicated topological spaces, and it's very difficult to imagine, except in dimension 1, one can draw things like graphs and trees, but in higher dimensions, it's difficult. And now we have these piecewise linear subsets called skeletons, and they are somehow approximations to the genuine topological space. So furthermore, Vladimir constructed a deformation retraction from the non-Archimedean space to the piecewise linear skeleton. Let me give a few remarks on this. This has intimate relations with tropical geometry, SYZ and SYZ fibrations in mirror symmetry. And it's this relation that suggests a non-Archimedean approach to enumerative problems in mirror symmetry. And motivated by, so this non-Archimedean approach was actually my original motivation for developing a theory of derived non-Archimedean geometry together with M Porta. And as I explained above, that there are plenty of recent active developments in non-Archimedean geometry, and they provide many other motivations beyond enumerative geometry and mirror symmetry. Okay, so this is a brief history and motivations. Are there any questions at this point? Okay, so now let's ask, so what is a derived non-Archimedean analytic space? To answer this question, let's first recall the definition of a derived scheme. Recall, a derived scheme is a pair X, OX, consisting of a topological space X and a sheaf OX of simplicial commutative rings on this topological space, satisfying the following conditions. So first, we ask that when we take pi 0 of this sheaf of simplicial commutative rings, we get simply a scheme. And the second, we ask that when we take pi j of this structure sheaf, this simplicial commutative rings, we get a quasi-coherent sheaf of modules over this pi 0. Yeah, so in some sense, we just ask that when we truncate, we get the same as a scheme, and then all the higher order terms have some finiteness conditions. So that's all.
May I ask a question?
Sure.
Do you assume that OX is a hypercomplete?
For schemes, I think it will be a consequence.
Okay, I think if you assume it's nothing, then it's a consequence. Wait.
Yeah, and thank you for the question. For scheme, yeah, it's technical. Let's talk about it. Let me think about it later. Yeah, so now we would like to adapt the above definition to non-Archimedean analytic geometry. So here in the definition, there's no analytic information at all. In other words, we need to find a way to impose additional analytic structures on this structure sheaf OX. So what kind of analytic structures? For example, we would like to have a notion of norms on the sections of the structure sheaf. And furthermore, for example, if we have convergent power series and we have sections of the structure sheaf, we would like to compose these functions with convergent power series. So these are the operations that we should be able to do in analytic geometry, but they are not provided in this definition of derived scheme. So we would like to put additional analytic structures there. And our first attempt is the following. We see that here in the definition, it's actually, as I said, it's very simple. It's just topological space with a sheaf of simplicial commutative rings. So our first attempt is just to enhance this simplicial commutative rings with some non-Archimedean analytic structure. In other words, we would like to have some sort of like simplicial commutative affinoid algebras or Banach algebras. If you are not familiar with non-Archimedean geometry, let me just briefly mention that in analogy with algebraic geometry, for example, for algebraic varieties, they are built from a spectrum of polynomial algebras and also quotient of polynomial algebras, called algebras of finite type over field. And yeah.
Looks like the bottom of your screen does not fit our screen.
Oh, so I can go. Now it's better.
Yes, thank you.
Yeah, I don't know. Sometimes there is some toolbar of Zoom which may obscure the bottom of the screen. I'm not sure. Sometimes when I listen to other people's talks, I also have something obscured. So if it happens again, please let me know. Yeah. Yeah, as I was saying that algebraic varieties are built from spectrum of algebras of finite type, and analogously in non-Archimedean geometry, rigid analytic spaces are built from spectrums of so-called affinoid algebras. And they are special types of Banach algebras. We are doing analytic geometry, so we need norm topology and so on. But it's very difficult to do actually, because this topological or Banach structure and the simplicial structure, they just do not mix very well. And there are recent works by Benbassa, Kremnitzer, Bambozi in this for studying these kind of objects. But when Mauro and I first trying to do it in like a few years ago, just it was hard. So our strategy is to use the theory of pregeometry and the structured topos of Lurie and completely circumvent this foundational issue regarding mixing simplicial with like Banach. The idea is the following. So the idea is to use the language of infinity category or infinity topos to generate derived sheaves starting from simple classical objects. And hence, we can bypass any model-dependent constructions. For example, simplicial algebras, DG algebras, and so on. So here, when we talk about simplicial commutative rings, they are, in some sense, just models for what we eventually want. And the idea is that by using this like more high-tech machinery of pregeometry and structured topos, we can just generate these infinite categorical objects directly from very simple classical objects, bypassing any considerations of like what kind of Banach structure to put on simplicial rings, or how to take a simplicial resolution of Banach rings. We can completely circumvent these model-dependent questions. Okay, so now let me explain briefly what is the content of this theory. Definition. A pregeometry, in the sense of Lurie, is a category T equipped with a class of so-called admissible morphisms and a gross-antic topology generated by admissible morphisms satisfying the following conditions. First, we ask T to admit finite products. Second, the class of admissible morphisms is closed under composition, pullback and retract. And we assume that pullback of admissible morphisms along any morphisms always exist. And the third, when we have composition, if G and H are admissible, this implies that F is also admissible. Yeah, so it's abstract notion. And here are the examples that are relevant for our purposes. We fix K, any non-Archimedean field, can be any characteristic. And we consider first T étal K, so a pregeometry T étal K. It's a category. So first of all, the underlying category, it's just the category of smooth K varieties. And the class of admissible morphisms is the class of étal maps between these smooth varieties. And then the topology, we put the étal topology. So we see that it's just straightforward. Étal topology is generated by étal maps, and product of smooth varieties is again smooth, and étal morphisms are very nice and also satisfies all the conditions. So this T étal K is an example of pregeometry. Next, just analogously, we define the analytic version of T étal K, denoted by Tnk. So now the underlying category is the category of smooth K analytic spaces, is smooth non-Archimedean analytic spaces. And the admissible morphisms are étal maps, and we put the gross-antic topology, the étal topology. Yeah, so we will build the derived theory, or the derived theory just starting from this pregeometry, like this pregeometry. And as we see that inside we only need to consider quite simple objects, these smooth analytic spaces. We don't even need to know like singular spaces, let alone like simplicial rings or so on. So this infinity categorical machine will produce for us automatically all the derived spaces, including all the singularities.
Can I ask what is an Italian map of analytic spaces? Do you require isomorphism on tangent spaces or something else?
Yeah, the definition, it can be given just completely analogous to algebraic geometry. For example, one can restrict to affine or affinoid pieces and ask the associated like map of rings to be eta. And equivalently, it can also be expressed as like some at the level of Jacobian of functions. The theory here, it's really parallel. Okay, so as I said, we have some infinity categorical machine, which automatically produces for us some derived theory out of this very basic classical input. What is this? Yeah, now we introduce the following notion, following construction, following Lurie. Now let T be a pregeometry and X an infinite topos. So if you don't know what an infinity topos is, you can just think of X as the category of sheaves of spaces on any given topological spaces. Now, a T structure on X is a functor O from T to X such that it preserves finite products. It sends pullbacks of admissible morphisms in T to pullbacks in X, and it sends coverings in T to effective epimorphisms in X. Effective epimorphism is just the right notion of epimorphism in this infinity categorical setting. Okay, yeah, so it's still quite abstract notion, and let me explain what's the idea behind this abstract definition. So the idea is that when we have pregeometry T, an infinity topos X, which we think of as the category of sheaves on some topological space, then we can think of this T structure, a T structure as some kind of sheaf of derived rings with additional structure coming from the underlying pregeometry T. So in the case when we apply the definition to this pregeometry of analytic geometry, then we can just think of a T on K structure O as a sheaf of derived rings equipped with an analytic structure. And that's exactly what we wanted from the beginning. Yeah, so how we think of it, how we think of this structure, which is a functor, as a sheaf. Well, so let's see, it's just a functor. There's no sheaf here. And first, in order to get a sheaf, we just evaluate the functor O on A1. A1 is inside our pregeometry. It's smooth. So we evaluate the functor O on A1. We get a sheaf F in X. And this is, in some sense, our structure sheaf. And this is not just a sheaf of sets, it's actually a sheaf of rings, because we have sum and multiplication induced by this functor O. So on A1, we have the sum operation, which is just map from A1 times A1 to A1. And since this functor O preserves products, it induces a sum operation on the sheaf F. And similarly, the multiplication operation on A1 induces a multiplication operation on the sheaf F. Therefore, we can intuitively think of F as a sheaf of derived rings, or if we speak like as using language, model-dependent language, we say simplicial commutative rings. Yeah, so we see that via only the property of product preserving, we get a ring structure on the sheaf. And next, we want analytic structures. So recall that we gave some examples of analytic structures, such as norm and the composition with convergent functions. And we can construct the norm on the sheaf as follows. So the sheaf F is also equipped with norms in the following sense. We consider D1 in A1 the closed unit disk. And that's also smooth rigid analytic space. So it lives in our category, in this pregeometry category. And we recall that in the definition of T structure, O sends pullbacks of admissible morphisms in T to pullbacks in X. And this implies, so we have this inclusion, which is, so this inclusion is also an Étale map. And by the functoriality, we get a map from OD1 to F, which is O of A1. And by the pullback property, we can deduce that this is actually a monomorphism. So in some sense, we get a subsheaf of F, and we can think of this OD1 as the subsheaf of F consisting of functions of norm less than or equal to 1. Yeah, so let me just recapitulate. Via this product preserving property, we get a ring structure on the sheaf. And now via this, the second property about sending admissible pullbacks of admissible morphisms to pullbacks in the topos, we get a subsheaf with bounded norms. So this gives us norms. And finally, if we have any convergent power series F on D1, by the functoriality, we obtain a morphism from OD1 to F. And we can think of this morphism as composition with F. So OD1 are all functions, like all sections with norm less than 1. Now we compose these sections with the given convergent power series on D1, and we get sections without conditions on the norm. So this is composition with power series, convergent power series. Yeah, so we see that using this nice framework of pregeometry and structured topos, we solved very quickly the problem of imposing analytic structures on these derived rings. And now we are ready to give the definition of derived non-Archimedean analytic spaces. So once we get this analytic structure on our structure sheaf, we can more or less mimic the definition of derived schemes and for the definition of derived non-Archimedean analytical spaces. Yeah, so here is the definition. A derived K-analytic space is a pair XOX consisting of here I put the word that was mentioned by Qing Yuan a moment ago. It's just a technical condition on the topos, and we put it for our convenience. So it's a pair consisting of a hypercomplete topos X and a T on K structure OX on this topos such that, so we put exactly the same conditions as in algebraic geometry. So we ask that if we forget the analytic structure and take pi 0, we just get like a classical non-Archimedean analytic space. So to be precise, we get a set equivalent to the ringed, or a topos equivalent to the ringed infinity topos associated to the Étale set of a classical rigid analytic space. And the second, just completely parallel to algebraic geometry, we ask that when we take homotopy groups of the structure sheaf, we get a coherent sheaf over the pi 0. So in algebraic geometry, we had quasi-coherent sheaf. In analytic geometry, quasi-coherent is more complicated to work with. And here we just put coherent sheaf, which is sufficient for our purposes. But if you need some analytic space for other purposes, maybe it can be replaced also by quasi-coherent sheaf. Okay, so yeah, so that's all. Here, that's how derived analytic geometry, how the notion of derived non-Archimedean analytic space is defined. And after introducing this notion with Porta, we proved many foundational properties, such as, in order to develop any theory, we need to work out basic properties such as theta acyclicity, and also like relations, like existence of fiber products, also notions for modules, coherent sheaves, like properness, like derivations, square zero extensions, cotangent complex, and so on. And we studied all these basic notions and proved the required properties. But then there is an important question to figure out, is that we have this fancy, introduce this notion of derived non-Archimedean space via this fancy machinery. But how do derived analytic spaces actually appear in nature? How do we construct them, or how we have the theory, but it's only useful if we can apply it, if these spaces actually are relevant in practice. And the answer to this question is that we can obtain naturally derived analytic spaces via the representability theorem. So this was like the first this was one of the theorems that we really aimed for. And here is the statement.
Sorry, before you state the theorem, may I ask a question about the definition?
Sure. Yes.
So if K is a usual field, like an Archimedean field, then this definition will corresponding to like a derived algebraic space, or?
Yeah. So if K is any field, then we don't have analytic structure. We only have algebraic structure. Then this definition actually corresponds to the Riemann-Forte stack. Yeah, we have proved this comparison theorem in one of our papers in this algebraic setting. But also, we have also studied the case where K is complex numbers, and we consider this analytic structure, but not non-Archimedean, just the usual complex analytic structure. Then this actually gives complex analytic geometry, some derived complex analytic geometry. But we didn't go very far in the complex setting because all of our motivations were from this non-Archimedean geometry.
I see. Thanks.
Okay, so as I said that now we have this nice notion, and in order to put it in use, in practice, we need some theorem which produces for us derived analytic spaces. And that is the representability theorem. Here's the statement. Let F be an analytic moduli functor. In other words, a sheaf over the ideal of derived analytic spaces. Then the followings are equivalent. First, F has the structure of a derived analytic space. And the second, F is compatible with Postnikov towers, has an analytic cotangent complex, and its truncation is a classical analytic space. Let me remark that the representability theorem has two important implications. The first implication is philosophical. It implies that our notion of derived analytic space is natural and sufficiently general. Because we see that by the representability theorem, any reasonable analytic moduli functor now has the structure of the derived analytic space. And this shows that our notion is sufficiently general to cover these cases of interest coming from moduli problems. The second implication is at the practical level. So the representability theorem shows that in order to check whether we get some derived space, the conditions are easy to verify in practice. I will just say a bit more about what are the conditions. So the theorem gives plenty of down-to-earth examples of derived analytic spaces. In practice, these conditions are very easy to check. Let me just remark that when we say that a moduli functor f is compatible with Postnikov towers, if it is infinitesimally cohesive and neo-complete, we are just following the terminology of Lurie. Infinitesimally cohesive means that f sends square zero extensions to pullbacks. Yeah, it's related to Schlesinger criteria in usual moduli problems. And the neo-complete, it's just that when we take limit, oh, I should put a limit somewhere here, of f applied to truncations, we get equivalence. So, and yeah, these are really straightforward to check for moduli problems in practice, and this shows that the theorem really gives plenty of examples of derived analytic spaces. Let me remark that we have also proved a generalization of the representability theorem for stacks. Here's an application of the representability theorem. It's for the existence of derived mapping stacks. Here, let's consider rigid analytic spaces, X, Y, and S. So when I say rigid, I just want to emphasize that it's classical, like not derived. So we have X, Y, S, X proper flat over S, and Y separated and LCI. Then we have the infinity mapping functor, map from X to Y over S, which is just given by the usual formula, like for any t over S, this functor, the value of this functor on t is just given by this mapping space from xt base change from xt to yt in the infinity category of derived analytic spaces. And then we showed that this functor actually satisfies the list of conditions needed for the representability theorem. In particular, we can construct an analytic cotangent complex. And then applying the representability theorem, we show that it is representable by a derived K-analytic space, which is separated and locally finite presentation over S. Here, I said the mapping stacks, so actually the whole thing can also be generalized to stacks.
Tony, there's a question in the chat. It says, can representability theorem be viewed as generalizing the Brown-Lurie to the case of derived analytic geometry? I
would say it's an analog of Artin-Lurie representability theorem. It's an analog of Lurie. He proved this. Maybe. Yeah, in some sense, we didn't really. So it's not a Brown-Lurie. There's Artin-Lurie representability theorem in algebraic geometry, in derived algebraic geometry, which starts from functor satisfying a list of conditions and shows the representability in terms of a derived algebraic stack. And it's different, it's slightly different from what we are talking about here, because here we assume that the truncation is the truncation is representable, but in the algebraic case, one can do better. One can remove this condition and put some a bit more these infinitesimal deformation theoretic conditions. In analytic geometry, it's probably also possible, but it's a different question, because it's like this is only, it's more of for some philosophical purpose. For practical purpose, this statement is good enough for applications.
I mean, actually, what happens if you plug T étal of K into your theory instead of T analytic of K?
Yeah, then one gets the usual dilemma for the stacks and the derived dilemma for the stacks.
And I mean, your theory of derived schemes is then the same as the standard one?
Yeah,
Yeah.
it's equivalent, and that's already written in Lurie's papers. This T étal. Okay, so now let's move on to more geometric problems about curve counting. So let's take a look at the modular stack of non-Archimedean stable maps. Let's fix X a smooth, rigid K-analytic space. So analogously, we can define the stack of stable maps, these non-Archimedean stable maps. For any base T, an n-pointed genus G stable map into X over T, it's just the same definition as in algebraic geometry. So it's first, it's a pre-stable curve over T together with a map such that every geometric fiber is a stable map, in the sense that its automorphism group is a finite analytic group. Now, applying the representability theorem again to this modular problem, we obtain immediately a derived enhancement of the modular stack of non-Archimedean analytic stable maps. So with M Porta, we showed a little bit more. We showed that it's representable. First, it's representable just as application of the representability theorem. Yeah, let me just read the whole statement. The derived modular stack, which we denote by R, mg and bar x, of n-pointed genus G stable maps into X, is representable by a derived K-analytic stack, locally of finite presentation, and furthermore, it is derived LCI, which means that the cotangent complex is perfect and is in tau amplitude from 1 to minus infinity. Since we would like to count curves eventually in X, we also need some compactness result. And I studied it a while ago. I proved that if furthermore, the rigid analytic space X is proper and has equipped with a Kähler structure analogous to Kähler metric in for complex manifolds, then given any curve class B, if we consider stable maps with given class, then the substack is proper K-analytic stack. And hence, when we equip it with the derived structure, we obtain a proper derived, this R just means derived, proper derived analytic stack. And combining properness with derived structure, we obtain immediately the non-Archimedean quantum K-invariants as follows. So now we just ignore, like forget about the classical moduli space. We just work with the derived one, and we consider evaluation maps and stabilization maps directly at the level of the derived space. Then the quantum K-invariants are immediately defined as we just, so for any classes in the K0 of X, we just pull them back by the evaluation maps, and we push down by the stabilization map. And this gives this quantum invariance that we need, that we hoped for. So here, let me just remark that quantum K-invariants in algebraic geometry were first proposed by Giventhal and constructed by Y.P. Lee. And in the algebraic construction, we pull back and we also tensor with the virtual structure sheaf. But here we are working directly at the level of derived geometry, and all the maps starts from the derived moduli space. So we no longer need this virtual structure sheaf. And this not only simplifies the construction, the definition, but also simplifies the proofs for the properties of these invariants. Instead of manipulating perfect obstruction series, as in the classical case, our study of the properties of the non-Archimedean quantum K-invariants is based on the list of natural and intuitive geometric relations between the derived moduli stacks, which I explain below. So in the classical construction by Y.P. Lee, the properties are proved based on properties of perfect obstruction series. And here, we no longer work with obstruction series. We just have this derived enhancement, and we can have a list of very intuitive geometric relations between the derived stacks, just as between the classical stacks, but somehow they are sufficient to give all the properties we need. So in order to state the geometric relations, instead of working with M-pointed genus G stable maps, we use a slight combinatorial refinement called tau beta marked stable maps for any so-called A graph, tau beta introduced by Barry and Manning. So this A graph is just a pair tau beta. Tau is a graph, and the beta are curve classes associated to every vertex of the graph. So the graph imposes degeneration types on the domains of the stable maps, and then the curve classes associated to every vertex imposes like what the curve class should be for the corresponding irreducible component. So given any A graph, we have associated moduli stacks of, we denote by M bar X tau beta of tau beta marked stable maps, and their derived enhancements are M bar X tau beta. We also consider, we are also able to consider relative situation when X is a family over some S. So here are the relations of derived moduli stacks. Let S be a rigid K-analytic space and X a rigid K-analytic space smooth over S. I just state the theorem in the relative setting. but you can just think of as absolute. Relative is just much more general and also convenient for later purposes. Then the derived moduli stack Rm bar. This derived moduli stack of tau beta marked stable maps into X over S satisfies the following geometric relations with respect to elementary operations on A graphs. Yeah, so these geometric relations are really intuitive to think. One can guess what they should be. First, it's called the products. If we have two A graphs and we take their disjoint union, then the moduli stacks is just a product. Second one called cutting edges. If we have a graph and we cut at an edge E, then it breaks into two graphs with these legs I and J. Then we obtain a derived pullback diagram. So the moduli stack associated to this original graph, it's just a pullback from the moduli stack associated to this cut graph, pull back along the diagonal. It's like we pull back along the diagonal, meaning that we are gluing these two legs. So here, let me emphasize that it's intuitive to think because at the level of classical moduli spaces, that's what it happens. But the content of the theorem here is that it's not just a classical pullback, but it's also a derived pullback. So in terms of it also contains all the information about virtual counts of curves. Similarly, we also have this property, universal curve property. If we have some graph, we forget the tail, then we get this derived pullback. And same context as above, we have this derived pullback. When we forget the tail, it's it's easy to see. It's easy to believe this derived pullback. And finally, there is the relation called contracting edges. When we have some graph, we can contract an edge. And furthermore, we can add some tails to this contracted edge. And given any integer L, positive integer L, we can go back and expand. Before we had just one edge, now we expand by a chain of edges. And we also compatibly distribute these new tails and the new curve classes. Then it's easy to guess that we should have also an equivalence between the associated derived stacks. So maybe I have one more minute. Let me just remark that, as I said, all these relations, they are very intuitive and easy to believe, but actually they contain all the information about virtual classes and virtual counts. So for example, the universal curve relation above, in the particular case where tau is a point, is the following. It just says that the forgetful map, forgetting the last marked point, is equivalent to the universal curve. So this is a for the classical moduli stacks, it's the statement that we are very familiar with. But now we are saying that it's actually also true together with the derived structure. And such an intuitive statement, in fact, incorporates all the information about virtual counts with respect to forgetting a tail. Yeah, so let me stop here. I just have 2 more remarks. One about also curve counting with multiplicities, and another about virtual classes and Gromov written invariants. So let me stop here, and thank you very much for your attention.
Okay, yeah, thank you very much. Let's thank Tony in the chat, or otherwise, yeah, good. Okay, good timing. So, right, let's see. So, are there any questions for Tony?
May I ask a question?
Sure.
The first one is just about the definition. Like the usual way of define, the like the manifold stack, the infinite tuples information encode the fact that in the ordinary field there is a Derived manifold stack. So in this case, that's your definition of analytic space also already have a like the manifold structure.
You are right. Yeah. So it already has. In order to compare, actually, we have proved the comparison theorem. Yeah. Here. Yeah. It already contains the Lin-Mumford, but probably with some bit of restrictions. So also in the classical case, to really in algebraic geometry, to really compare with the Lin-Mumford, one has to add some condition of being n localic to the topos, to the infinity topos.
Yeah.
So here I think it's similar, and yeah, so somehow when we apply to enumerative geometry, let me see, what did we write? When we apply to enumerative geometry, here we are saying it's representable by a derived stack. Because in general, we know that even the moduli space of stable maps is only an Artin stack. So yeah, but in the case when it's the Lin-Mumford, when like it's over characteristic 0 and we get the Lin-Mumford stack, then actually here we can just say a space. But it's not I mean stack space. Yeah, not here. You are right. It already allows a little bit of automorphisms. I think.
I see. Like in the statement in the representability theorem you state, so the underlying space is a analytic.
Yeah, somehow it's just this amount of automorphism is completely determined by the underlying
one.
Yes.
Okay, great. I also have a question that so you mean this formalism of this derived the stack of the ground written moduli space in this formalism can take place what usually the perfect obstruction theory does. So does it I mean I just want to ask is the place of the usual perfect obstruction theory the role of the usual perfect obstruction theory replaced just by the ordinary just by the cotangent complex, or is the role replaced by something else?
Yeah, when we have derived LCI, so a usual when we have a derived structure that is also, as I defined, derived LCI, meaning the cotangent complex is perfect and concentrated in like in the case of space, it's just in 2 degrees, but in the case of stacks, we allow like 1, 0 can also be unbounded in the other side, the other direction. Yeah, then this induces a perfect obstruction theory. And all perfect obstruction theories coming from natural moduli problems come from this derived enhancement.
Okay, I see. So
Yep. Perfect abstraction theory depends on the choice somehow.
yeah.
And derived enhancement, it's somehow, once we formulate the moduli problem, then it automatically has a derived enhancement.
Yeah. Yes. Yeah. Yeah.
Yeah, perfect abstraction theory, it's
mm-hmm.
an application of intersection theory in algebraic geometry, which so for the same moduli space, one can somehow choose different perfect abstraction. There's no canonical choice, and yeah, then one has to have compatibility of perfect abstraction theories, and but there's one advantage of perfect abstraction theory is that it's really quick, that to produce the virtual fundamental class, and also sometimes, since we have choices, it's not canonical, have choices, so sometimes we can choose choose some simpler ones. It's also a great technical tool.
Yes, and I'm just wondering that because in the classical intrinsic normal cone theory, that they use perfect operand theory to construct a virtual fundamental class.
Yeah. So here maybe I should point out that why we are doing this derived geometry in the non-Archimedean setting is that the classical abstraction theory do not fit very, very well into the analytical world.
I see. So I mean, what is the what replaces the role of the virtual fundamental class here? Is the structure change?
Here I haven't talked about virtual fundamental class, but so there is an extra step for making virtual fundamental class, and because one reason is that in analytic geometry we don't have Chow groups, Chow rings. We don't have intersection theory as simple as in algebraic. I mean, not so algebraic geometry, not so simple, but we don't really have intersection at the level of cycles. So it's a bit more complicated, and but this is not the important part. I mean, this is not essential, because it's just an extra step to go to virtual classes, and then all the properties will follow from this list of geometric relations again. Just one more functor to go, but all the properties again follows from the list of these geometric relations.
I see. Okay, great, thanks.
Yeah, thank you.
Great. There's a question in the chat about maybe you could read it.
Yeah, so this is a very natural question, and the relations are studied by Giventhal. There's no simple relation. It goes through a quite complicated formalism of Lagrangian cones and this, and there's no explicit formula yet for the relations. And what's mirror symmetry for quantum K-invariants? This I'm not sure. I think quantum K-invariants probably have more applications in representation theory. And on the mirror side, what they should do, it's not yet clear.
Yeah, thank you. Any more questions to Tony before we go to Gathertown? Can I just ask a quick philosophical question, right? So when you do this curve count on non-Archimedean spaces, is it because we care about degenerations and want to do like degenerate the complex variety and then count curves, or it's because we'd like to do curve count on non-Archimedean spaces themselves.
Yeah, that's a great question. I mean, it's really motivated by degenerations. So in mirror symmetry, we study not just single Calabi-Yau varieties, but degenerating families. And then very naturally, we obtain non-Archimedean space defined over the Laurent series field. So yeah, so that's how non-Archimedean geometry comes into the picture. But maybe, I don't know if it makes sense to study also curve counting for p-adic variety spaces. This it's currently, I mean, people don't even have conjectures of what will happen, but maybe one can try it like later.
Okay, thank you very much. So let's thank Tony again for the nice talk and answering our questions. So we'd be meeting in Gathertown now. So there's a link in the chat. Please come along if you'd like to chat with Tony, and also if you have any ideas about the future of the seminar and future speakers and so on. So I'll hope to see some of you there. Tony, can you come for like a little bit now?
I'm already there.
Ah, you're already there. Excellent. All right. So see everyone there.